But at the moment, you have about 1 to 2 terawatts of biomass fuels coming out. And then you have the whole area of photothermal, whether you can start making new materials that can harness thermal energy more efficiently. And the potential is there for about 2 terawatts. But solar, which is there everywhere around us, has the largest potential. It has 3 problems associated with it that need to be tackled. One is capture. How do we capture light? How do we absorb enough light to be able to convert that light into photocarriers? So it's not just capturing things, but you also need to efficiently take the photons that are coming there and create electron-hole pairs. Once you have that, you can also talk about the storage, which is another huge problem in its own. And it's an area that I probably wouldn't want to touch at the moment, simply because time is limited in what we can do. But if we want to create photovoltaics or solar cells, we need to be able to use the light to create the electricity. And the fundamental issues that we are trying to fulfill are photogeneration charge carriers being absorbed into the material and separating them out. Now, there are many technologies out there that is doing this very thing. But we do know that all of these technologies that are above here, or many of them, are very, very expensive. It's expensive because you generally tend to use crystalline silicon materials that are hugely expensive to produce, and you are looking at thick materials when it comes to crystalline materials in order to absorb things. If you take a crystalline silicon solar cell, you're effectively talking about 200-300 microns of material that has to be used in order to absorb things. What we want to do from our lab's point of view, and many other labs in the world, is to look at the 4th generation of solar cells. So these are the first generation of solar cells that came out, and then you have the 2nd generation of solar cells that are based on polycrystalline films. But this 4th generation that are based on organic materials are very, very cheap to produce. The only problem here is that the current efficiency is around 5%. And the question is, can we improve the efficiency to close to 10%? So, as indicated, you have the 1st generation single crystal, 2nd generation amorphous silicon, polycrystalline silicon based materials. The 3rd one had the dye-synthesized solar cell, the polymer solar cells. But the 4th generation one is looking at the hybrid materials. And what is a hybrid material? A hybrid material really is looking at making the solar cell that generally has to be a few hundred microns thick much, much thinner. What it's trying to do is to create nanoparticles, nanostructures within your material that fools the light into thinking, oh yes, I've got enough area here in order to absorb the photons that are hitting that. Now, in order to do that, you need a matrix that is highly photoabsorbing. And the matrices currently that are being looked at are based on organic materials. And these organic materials, when you have nanoparticles associated with it, effectively fool the light that is hitting it to think that they are single crystals. They are single crystal materials that can absorb, and then what we need to do is have means in which we can transfer the charge quickly from the absorbed light into the electrodes. We are also trying to use various polymer systems, and in this case, typically you would use something like a fullerene PCBM, a C60 based material, as an acceptor, and you'll have P3HT or copper phthalocylene or many of the other materials as a donor material. And you're trying to make materials that are solution processable so that you can start making these things inexpensively as paints. Now, when you start looking at these materials and then looking at how it can be applied to structures, the other issue that you need to start thinking about that is extremely crucial is how does your photon get absorbed and what happens to the carriers that are created. The problem is quite simple, that if you have a material such as an organic, you need to have something between 100 and 200 nanometers of material in order to absorb enough carriers. Right? Now, think of the numbers we're talking about. Here we are talking about 100 to 200 nanometers. In crystalline silicon terms, we were talking about 100 to 200 microns. Right? Suddenly, if we were to look at it from this scale point of view, your crystalline silicon would have started there and it had gone all the way down, 1,000 times larger. So we've decreased the volume hugely. But when you decrease the volume hugely and have these materials that are hugely absorbing, we have a problem, because once you create your absorbed electron hole, which is called an exciton, those excitons cannot diffuse very far. They can only diffuse to about a maximum of 10 to 15 nanometers. So there's the problem. You need to have 100 nanometer thick material, but its diffusion length is only of the order of 10 nanometers. So in order to overcome the problems associated with the third generation polymer solar cells, people had to come up with heterojunctions or nano-heterojunction solar cells that allowed you to have a blended structure. That blend allowed you to have these heterojunctions or heterogeneous media next to each other, but have enough of a thickness of a material in order to absorb things. So similar concepts have been used when it comes to, say, dye-synthesized solar cells or the Grätzel cells. And in the case of Grätzel cells, once more, you can start looking at titanium dioxide. And these are very good photocatalytic material that enhance the redox process. And again, nanostructured materials there that can allow better absorption of the photons that are hitting it and thereby allow the charge transfer. So the ideal structure many people are aiming at is actually shown in this diagram. And the diagram is, can we create a thin film solar cell where one of the electrodes are three-dimensional rods sticking out, say for instance maybe zinc oxide based rods, and put an organic material on the other side with an electrode on the other side. And this would give you the largest packing density possible of these heterojunctions that can allow efficient charge capture, dissociation, and transfer. And so that is where people are trying to get through using different routes. There's also another issue then that comes in. And this is also quite a significant issue. When it comes to organic materials, your absorption band in the electromagnetic spectrum is quite narrow. You're typically talking about visible lights with narrow bandwidth in terms of absorption. So you need to think about, am I utilizing this material in order to absorb everything that is out there or not?